Sí, vamos a lanzar una bomba atómica sobre el instituto.
It is titled as Symmetries and Optical Models.
Actually, optical models and symmetries. I'm sorry. I'm very happy to be talking here because Natig has been a close friend for many years. And by close friend, I mean that not only have I been present when he's beaming his good disposition, but also when he's angry. And that's why I value him more. Right?
Angry with what?
Angry with me. Okay. So, this is you can call it a promenade through some of the symmetries that we have been considering. Now, the first few slides, you see we have 30 papers in common. So I'm not going to tell you exactly what each one of these contains, but I'll try to give some kind of resume. The last one is with Professor Area, and there's also Mesuma, there's also Metin Arik, and many other friends. So, this is the general structure of the talk. We will start with the Euclidean group, which gives the geometric and wave models of light. From there, we'll make a contraction to the Heisenberg-Weil group, where we have the paraxial models. The paraxial models is when optics looks like mechanics. But of course, optics is much more rich than mechanics, because mechanics has kinetic energy and potential energy, summation. But optics is more eclectic. Then, you see, we make a quadratic extension. And here we have a lot of gold in the pot, because we have linear canonical transforms, which has also have a lot of attention in many fields. It includes thin lenses, small angles, but also canonical transforms. Then the compact subgroup of that is the Fourier group. And I think we had some incidents on the Fourier group, because the Fourier group is common not only for continuous optics, but for discrete optics in pixelated screens. It includes rotations, gyrations, and Fourier transformations. Then, if you look at the covering algebra of that, well, we get nonlinear, well, essentially linear, but you can understand it also as nonlinear aberration group. And there we can propose classification, composition, and aberrationless Fourier transforms. And then, you see, this is the mother group of optics, and this is the grandmother group. It's a version of discrete optics. It applies when you have finite data points, pixelated screens, which you can rotate, gyrate, aberrate, and do whatever you want with them. So, in the beginning, there was symmetry. Perfect symmetry. Now, of course, you may think, well, it's trivial because it's the symmetry of perfect vacuum, nothing in it, of empty space. Well, this is the symmetry of empty space. It's a 4x4 matrix. Here we have rotations and translations, and of course the product. Now, it was seen that symmetries form a group.
By whom? Because you said that there wasn't anything except symmetry.
Oh, well,
seen.
You see, symmetry created in 17 days the rest of the rest of science. So, okay, of course, they form a group. I don't have to explain each one of the lines. And it was called ISO3, better known as the Euclidean Group. And there we have some fundamental objects, which are determined by their symmetries. Can you see it? Yeah. Well, if the symmetry group is translations along a line and rotations around that line, what you have is a line, right? So the Euclidean group, well, it's a coset within the Euclidean group, and the space of cosets is the space of all lines, directed lines in space. And that's your initial material. On the other hand, and here I think well, it's a problem with the projector, but your fundamental object can be the xy plane. And you can take that as a coset. And, well, the space of cosets is a manifold of all planes in all directions. And out of that, you can make wave fields, polychromatic wave fields. So, rays in geometric optics is a manifold of ray cosets. And here is the symmetry. So you have 4 coordinates and a sign, because you always have a screen. So you can decide, well, what is the position, what is the momentum of the ray. These, you see in optics, ray momentum is the angle, is sine theta times the refractive index. On the other hand, if you are working with polychromatic wave optics, then the manifold of planes has, this is the direction of a plane, this is the distance at which it is, over here. Now, well, you eventually bring this to the Helmholtz equation. This is a Casimir operator, and so you can, if you reduce yourself to the space of, with the same value of k, you have the space of Helmholtz solutions. Now, there's some postulates for geometry where you also introduce dynamics. The first one is essentially that rays are continuous and piecewise differentiable. dq, q is the coordinate, by ds is the magnitude of momentum, and you can write this as Hamiltonian, and here the directional derivative. So you introduce this Hamiltonian. Now, the dynamic postulate is when you say how the ray direction changes in linear response to the gradient of a scalar function over space called the refractive index. And from here you get conserved quantities. One of them is rays don't disconnect, and the other one is the Abu Sa'ad al-Allah ibn Sahel law of refraction, better known in the West as Snell's law, which was done 600 years before in the Abbasid court of Baghdad. So now some things can be made with geometric optics on phase space. One of them is a result which is very nice, I think. Well, you can have Hamilton equations, you can have canonical transformations, and you can factorize refraction on surfaces by a theorem by which the operator which passes you from rays in this space to rays in this space, referred to the same screen, can be factorized into root transformations. Each one of them depends only on one of the refractive indices, n and n prime, and both are canonical. So now this root transformation serves very well because you can clear some of the problems that you have when you want to describe refraction by arbitrary surfaces. Now, in Helmholtz optics, we have also some results. First of all, the manifold of monochromatic waves in space can be mapped onto functions on a sphere. Now, and this is called the, we called it the wave transform with Pedro González Casanova. And you can solve some problems. For instance, finding the Helmholtz wave field, which has the minimal energy and that passes through a finite number of points that you can specify. And concurrently, you can also have a Hilbert space with a non-local measure on the screen. The screen is a two-dimensional manifold. There, you know the value of the field and the normal derivative. And the Hilbert space is made out of non-local measure, which you don't often find in mechanics. On that, you can make relativistic transformations. You relativistically transform the sphere, and this is how we started interacting with Natig, Atakishiyev, and Wolfgang Glasner in 1994. That is how much? Almost 28 years ago. Am I? Yeah. Okay. We're still working on this, actually. You see, experimentally, what would you expect? Well, imagine that you're in a spaceship and you find another spaceship coming. And, well, you have a camera. So you take an instantaneous picture. Now, your camera was focused at rest. But the other spaceship is going at a relativistic speed. So what you get is a chromatic phenomenon. The image changes. So the relativistic comma aberration has to do with this. Well, this is a sphere. If you go fast, stars tend to focus, well, to concentrate on the pole of motion. If you've seen Star Wars, well, whenever the spaceship goes over the speed of light, you see the stars going to the center. This is what happens with a patch of phase space. You see, these are lines, and after relativistic transformation, you get these ones. So phase space deforms canonically, and each point of light generates a chromatic phenomenon, which we started out with that. Now, yes, for the Helmholtz wave field, well, your Hamiltonian has this form. This is a second-order differential operator. Your functions are value and normal derivative. So the generation of relativistic boosts looks like this, and all you have to do is exponentiate this. Well, we're still working on that. The exponential of one operator like this can be put in a closed fashion, but to actually compute it, say for Bessel functions, which are the minimal width of wave functions, that's a major problem. But here we have some pictures of this. You see, this is the original wave field. It's a Bessel function. And as you accelerate, here, you get this chromatic phenomenon. This is presently the thesis work of Cristina Salto Alegre. And the paper we did with Natig, you see Wolfgang Glasner had a computer, symbolic computation algorithm. We used Gaussians. Gaussians are not Helmholtz wave fields. But these are the things we could compute. So we presented some results on that without using Mathematica. No? What we have is whenever you translate from the optical axis, your sphere catches a phase, and then when you make a relativistic transformation, the sphere deforms, and you have to integrate over that. So we have to integrate. Mathematica is very slow in that. Now, contraction. You see, well, okay, so Euclidean group contracts to the two-dimensional Heisenberg-Weil algebra. These are the generators. So you get Heisenberg-Weil and rotations. Now, maybe the paraxial regime is not very interesting. That's what all students learn in Optics 1. But you can have the quadratic extension. So you can treat this classically or quantum mechanically because both regimes follow each other. You have these 10 generators. This is the Poisson bracket relation. You have them canonical. So you obtain the 6 symplectic conditions, which include, well, that the submatrix, this is a 4x4 matrix. So you get these symplectic conditions, and you have the real symplectic group in 4 dimensions. Now, this has 10 parameters, and I think it has bedeviled optics people for generations, but there's a simple classification for it, and that is the maximal compact subgroup of the symplectic group is the 4-dimensional group of rotations. And these rotations include the isotropic Fourier transform, which commutes with everything, the anisotropic or antisymmetric Fourier transform, rotations, and gyrations. And you can represent this on a sphere. And I think it's...
In some sense, it's analog of the dynamical symmetry, right? Because quadratic, exactly.
Well, it's something between dynamic and geometric. I couldn't really say it's dynamical. But to classify it, it's...
But oscillator case, dynamical is exactly in terms of the quadratic, right?
Mm-hmm. Yeah.
So, in that sense...
Well, it looks very much like a harmonic oscillator, of course. But for instance, well, rotations will rotate your screen. Gyrations will turn Hermite-Gauss beams into Laguerre-Gauss beams, and the like. Well, these are the generators. You see, this is a two-dimensional harmonic oscillator. This is a two-dimensional oscillator in X minus oscillator in Y. Gyrations are cross transformations between momentum in X position in Y and momentum in Y position in X. And plane rotations. Now, you see, well, this was geometric optics. When you have the wave model, you introduce linear canonical transforms, of which Turkey is one of the world centers of linear canonical transforms, based in Ankara, and also in Ireland and Taiwan are centers that study this. Now, okay, I don't have the time, but you see, Moshinsky and Christian Ken in 1971 introduced this. There was another optics guy who also found the kernel. He didn't find it as a group. And this has given well, there's a metaplectic sign here. Optics people don't quite understand the metaplectic sign, so we illuminated the whole universe of optics with some group theory. So, this is the integral kernel. The normalization constant has a square root. And when it has a square root, it means that you have a double valuation. But the symplectic group is infinitely covered. But when you try to make product of two, then you have to resolve this sign somehow. And well, if you resolve it, you save a line. Now, you have aberrations. Most people are afraid of aberrations. But if you classify them using the harmonic oscillator, everything is fine. So these are the generators of aberrations of rank k and weight m. They have a nonlinear action. You can apply them to position and momentum, and you get this whole series. But you can make a group out of that. You see, here you have aberrations. Here you have paraxial transformations. And you can define aberrations up to rank 3 in that case, canonicity up to rank 3 in that case, and you can find the product law, and that covers 2 or 3 pages of text. But it's a well-defined classification of aberrations. You see, because Ludwig Seidel, in 1851, I believe, he called them Bildfehler. Bildfehler means error of images. And he only considered positions because he was interested in forming images. However, you want to work in phase space. So the classification is slightly different. You introduce one more classification at one more aberration at each rank. It's an aberration that does not change the point where the ray touches the screen, but the direction in which it touches the screen. So you have a complete classification of aberrations. And of course, well, we've called ISO 3 the mother group. The name has not prevailed because scientists are very conservative. Now, the Euclidean group is itself a contraction of a grandmother group. A grandmother group of 4-dimensional rotations. So what can you do with that? Well, okay, so you write it, and here is proof that contraction brings you back to the Euclidean group. But in the one-dimensional finite oscillator, now this is where Natig and I and other people contributed, because Natig knew about Kravchuk polynomials, which I did not. But we both knew about rotations. So actually from the rotation group, you can build a finite oscillator. These are the wave functions. They're given by Wigner-D functions of angle 1/2 pi, because position and momentum on a sphere are perpendicular. So you have a pi/2 rotation, and these are the wave functions. So this is the ground state, you all recognize. First excited, second excited, but you have a top state. The top state is the ground state, just exchanging signs between each neighboring points. So this reflects this, but with change of sign. And this is the state in the middle. So this is the finite oscillator. You can have it in any number of dimensions. And basically, you're speaking about rotations. But in 2 dimensions, there occurs an accident. Ta-da! You see? It splits into a direct sum of 2 SU2 algebras. And not only that, but it has 2 chains, you see. Here, you can have it, like in the previous case, as a direct sum. Here, you have still a subgroup. On the other hand, SO4 also contains SO3, contains SO2, which is the normal Gelfand Zetlin chain of subgroups. So you can have a Cartesian basis and a polar basis for the 2-dimensional oscillators. And
except that you should emphasize the relation between SU2 and SO3. You mean that everybody knows that, right?
Yes, yes. I'm sorry, SO2 and SO3 as algebras are the same.
No, in different lines you use different notations.
Ah.
In that sense.
Okay. Well, so the 2-dimensional Cartesian basis is, well, harmonic oscillator. These are pixelated screens. I believe it's 32 by 32. Ground state, first excited state, second, and so on. You go up. Here you have a checkerboard of signs. This reflects this one. This is the middle one. Here, well, all the estrias go one way. Here they go the other way. And that is the polar basis. Ground state, first excited, second, and so on. And here every pixel changes sign. Now, these wave functions are Kravchuk functions. These wave functions are Clebsch-Gordon coefficients. So you have Clebsch-Gordon coefficients as wave functions. And, well, some people seem surprised, but these are Hahn polynomials. And, well, Natig knows more about Hahn polynomials than I do. But with Clebsch-Gordons, we're... no, I'm serious. Don't laugh. Come on. Okay, so we have square screens and round screens, circular screens. Now, what we can do is, for instance, we have the Cartesian basis. Out of these, we can import a change of basis to angular momentum and energy. So here you see that if you think of this as a particle, here it likes to go in one way, here it likes to go on the other way, and here it goes on the diagonals. Now, you can identify these states with these states. And what you get is a unitary transformation between square screens and round screens. Unitary, which means it's reversible. Now, of course, our institute always says, get out a patent, do applications, something useful for society. Well, you see, if ever Nokia decides to sell circular cell phones, maybe we can get some windfall out of that. Now, so recently we've also looked at rectangular pixelated screens, and that is because, you apparently lose some of the symmetries, but actually you can do the same thing. In this case, the the Cartesian basis is orthogonal. Well, all these are orthogonally complete. You can also do entangled states, because after all, this is a finite thing that you can put into a quantum picture immediately. So, in the Cartesian basis, here you have, well, there's 77 here, which corresponds to angular momentum 3 and 5. So we can define Laguerre-Kravchuk modes on rectangular screens. Namely, these, if you take one of the previous, say, where you have 5 here, 1, 2, 3, 4, oh no, here. You see, here you can accommodate 2 lines, and over there you can also accommodate 2 lines. You can pass from Hermite-Gauss wave functions to Laguerre-Gauss functions. These are, well, the rectangular screens. This is the absolute value. These two have the absolute value, but the phase is different, which means that you circulate in one way, or you circulate kind of radially. Here it's purely radial. And, well, this was a recent thesis by Alejandro Ursúa. So, I would say these are, call them new discrete functions, 2-dimensional ones, and call them Laguerre-Kravchuk. Why not? So, this is a complete basis of Laguerre-Kravchuk functions. So, again, you have the ground state, the top state, and well, all the ones, all the intermediate ones, and here they have the states with the same angular momentum, which we did not have in the case of square screens, but they're not, well, they're degenerate in angular momentum, but you differentiate them by energy. And on these, you can also define the Fourier group on pixelated screens. Fourier transformations are, you can call them domestic, because they're based on the Kravchuk basis. The rotations are imported from the continuous case, and so are gyrations. So you can rotate images on a rectangular screen. Here is a letter F. Here you get oscillations. Now that's inevitable when you have unitary transformations. So you go from here to here, you apply another rotation. This makes 90 degrees, but you see, since the screen is not square but rectangular, you get some of these oscillations. But when you reach 180 degrees, you get the same image perfectly. And well, this we did for this kind of patterns, so you also get it. Here, I mean, this square is different, just to check that we get the same one over here. Now, all of the interpolation, all the algorithms to rotate images, say, on television, whatever, sometimes you see a scene going around, they work with interpolations. Now, if you interpolate, you cannot compound interpolations, because you degrade the image. For instance, Matemáticas has 19 different rotation algorithms with different interpolations, but none of them is unitary. Now, this is unitary. Well, and here we have rotations for all of these modes. These are the ones that I showed you previously. You see here we have 3 bands, and also here 3 bands, but they're somewhat different. In the intermediate region, you have this sort of rotation, and in the top region, you have that form of rotation. Now, the virtue, of course, is that no information is lost. You can rotate back. Now, the sin is that it's the slowest possible algorithm for rotations. Why? Because every pixel in the rotated screen depends on all the pixels of the original screen. So if your screen is n by n, your algorithm grows as n to the 4th power. So maybe we can turn the sin into a virtue by saying, well, but you don't lose anything. And this is the same for gyration, you see. These are the absolute values, and these are the phases. Here you rotate, you gyrate the 5 states. This is one of the previous slides. In some of the intermediate states, you can gyrate in this way. In the top states, since this is absolute value, you have the same picture as above, but the phases are different. This phase is almost continuous, and this one changes sign between every two neighboring pixels. And I think we have some pending matters in case anybody wants to think on that. You see, we've dealt with pixelated pixelations that are Cartesian or polar. But if you want them hexagonal or any other pixelation, it's not so clear, actually. With Professor Arik and Professor Klimik, when he was here, we used Q algebras. However, with Q algebras, the distances between pixels is different. We only did it in one dimension. I mean, I think it's interesting, but it's not the full freedom one would like to have almost random points and have images on that set of points. We've tried rectangular screens and annular screens, but that didn't work. Student showed it couldn't work. I'm very grateful to students who show that one is in error. We also have aberrations in 2 dimensions. I won't have to explain this roughly. The images are too small. You see, this is a rectangle function. And this is the Wigner function on position and momentum. Now, we have a classification of all aberrations for one-dimensional signals. And another student is working on aberrations on all two-dimensional signals. And of course, say if you have a one-dimensional signal of n points, the total number of transformations is n squared. Now, this is a subgroup of the UN group that includes all, say, permutations of values. That's a big group. So we haven't quite gone into that yet. The Wigner function is another point where we collaborated very nicely because Wigner worked on the Heisenberg-Weil group. And I think most people all over the place have always considered the ordinary Wigner function based on the Heisenberg-Weil group. Now, this Wigner function is based on the rotation group, on SO3. And you can define a Wigner function on any group, any Lie group. Any Lie group where right and left invariant measures are the same. Now, with Tariq Ali, are you a co-author? Yes, I think. When Tariq Ali was here, because we did also the Wigner function for the affine group, where that condition on the measures doesn't hold. And, oh yes, and now we're dealing with Czernicke functions. Well, people here that know more about polynomials than I do, but we know a couple of things about the superintegrability. Other pending matters are cryptography, colored screens, entangled pixelated states, and other problems that we can find on the road. So I hope this talk has taken you through an autopista, autobahn, highway among mountains, and we didn't have to scale any of these, just giving a lot of pictures. And well, these are the happy people of Cuernavaca working on that. For some reason, Natig is not on, but you see, these come from other places. So, thank you very much, and I hope I see you in optics sometime. Well, that's it.
Any questions, please?
Maybe comments?
Why I wasn't invited to this event?
Actually, well, I can tell you.
You don't need to answer.
No, well, so let me put the previous one. Okay.
If there's no more comments, yeah, you can thanks again.
Thank you.
As closing, oh, yes, yeah. If you allow.
Maybe you want to speak into this.
Okay. Do I need?
You don't need a pointer, but.
Yeah. Okay.
It's working. It's nice.
Is it? Okay. So I just keep that. Yeah, most of you been yesterday at the dinner, right? So I think that I expressed my already gratitude to all of you, but I will repeat it now. Again, thank you for coming. Thank you for participating at this event, which was not my idea at all. And sincerely, at the beginning when the two people, actually, Jawad Snusi and Pepe Siade, who are directors of our institutions, suggested me, my first reaction was that to refuse that. I mean, so. And particularly because they said that take into account that we don't have a lot of money actually to organize that. So I was thinking that how I invite people and tell them that there will be no money to come actually and to cover your trip here. So at some stage but then I thought that, okay, I didn't have strength to reject this idea. So, I mean, and now I'm happy that I did not. So first, thanks again to Pepe and Jawad for this idea. And they then suggested two people who will organize that. And it was Carlos Villegas and Manuel. And I want to thank them both. They were so kind and they were so patient that some people never responded to these invitations, and so something like that, right? But they were still working, and sometimes even not telling me that, well, it's not easy actually to gather people. And of course, I'm very grateful that contrary to this fact, financial situation with this conference, so many people came. Thank you. And especially I would like to mention my co-authors who are here, Ivan, Renato, Metin, Bernardo, Decio. So you see, I am happy that I had chances to know them well, to work together. I enjoyed that actually, and I was really lucky to meet so many bright people because this list not complete, and I got messages from other people with whom I just collaborated. Explaining that they cannot come, and so they could not come, so whatever. So thank you for all of you. And did I forget to mention anything, or please remind me if I did. So thank you. And again, as I didn't know how to react to, I mean, all of you and coming here, and what I can do in response. So I mean, to pay back. So, and I remember I told one of them, of my friends, close friends, that just what came to my mind immediately. I said that whenever will be event related with your name, and I will be alive at that time, I will be one of the organizers of that. So I can repeat this, I mean, phrase to every of you, okay? Thanks again. Thank you.